In this video today, we're going to be looking at the basics of what is known as implicit differentiation. And all the work that we're going to be doing today is going to come from our textbook section 2.5. By the end of this video, you should be able to accomplish two things. You should be able to find derivatives using a new technique called implicit differentiation, and you should be able to also write equations of tangent lines to implicit functions. Now, before we can accomplish these goals, let's try to understand exactly what we are talking about when we're looking at implicit functions. So far this year, all of the functions that we've been working with have been written in terms of the independent variable. So for example, they've all been written in terms of y equals f of x, like the example I gave there, y equals x squared minus 3x plus 5. Implicit functions are usually given in terms of both variables at the same time. So in other words, it's not going to be written as y equals a function of x. We might see something like x times y squared equals 5. Now we could go ahead and try to solve for y, but if we tried to do that in this problem, we would actually get two different functions. We would get one where y was equal to the positive square root, and then one where y was equal to the negative square root. And so we would have to find two different derivatives to basically find the derivative of that implicit function. But implicit differentiation avoids all of that work. It lets us leave the function as an implicit function. And as long as we follow the process, we'll be able to find a single derivative that's going to encompass both scenarios at the same time. So as we're walking through our examples, there's a couple things that we're going to be doing to complete this task of implicit differentiation. First, we're going to assume that y is a differentiable function of x. So in other words, when we take a derivative of y, we can differentiate it with respect to x. So y prime is the same as dy dx. We're also going to differentiate both sides with respect to x, and any of the rules that we've learned this year will apply. Product rule, quotient rule, chain rule, power rule, all of those good rules are still going to be used as we're working through the problem. Once we have both sides differentiated with respect to x, we're going to get our final answer by solving the resulting equation for y prime or dy dx, depending on what you used for your notation. So these are basically the steps that we're going to follow. So let's look at a couple examples of this process in action here. We're going to start out with a basic example here. So in this problem right here, it's an implicit function because my x squared and my y cubed are on the same side of my equal sign. It's not written in terms of y equals f of x. And when I go through the process here, instead of using y prime, I'm going to use dy dx because I find it just stands out a lot easier. And I also don't want to mix up y prime with y to the first power. So I like to use dy dx as my notation for this. So I'm going to basically leave the function the way it is. I'm not going to try to rearrange anything. And as I'm working through, I want to differentiate both sides with respect to x, which means I'm going to take the derivative of every single piece of this equation. Now, when I differentiate this with respect to x, the derivative of x squared is just 2x, because I'm taking a derivative of x with respect to x. And if we think about that, that's dx dx, and that would just be 1. So anytime we take the derivative of an x term with respect to x, it's just really the basic power rule that we've been looking at. But what's happening over here in this one is now I'm not differentiating a variable x with respect to x. I'm differentiating y with respect to x. So I'm actually going to apply the chain rule on this guy, where I take the derivative of the outer function using my power rule. So I would get negative 12y squared. And then I have to multiply by the inner function. And in this case, my inner function is y. So the textbook will put this as 12y squared times y prime. Again, I like to use dy dx to show that I'm taking the derivative of y with respect to x. And then when it comes to solving the equation for y prime or dy dx, I find it's just easier to find the dy dx's than it would be to hunt for my y primes. So I took the derivative of the first piece with respect to x and got 2x. I took the derivative of this second term with respect to x and got negative 12y squared dy dx. going to put my equal sign, and then I'm going to take the derivative of 36, and we know the derivative of a constant is 0. So that's our first step, is to take the derivative of both sides with respect to x. And then our next step is to solve the resulting equation for y prime or dy dx, which just means you want to get the dy dx all by itself. So you're going to use your basic algebraic techniques to rearrange your equation. So I would start by subtracting 2x from both sides to isolate the dy dx term. So that would leave me with negative 12y squared dy dx equals negative 2x. And then, again, my goal was to solve for dy dx, so I would divide both sides by that negative 12y squared. And that would leave me on the left side with just dy dx. And on the right side, I would simplify that resulting fraction. Negative 2 divided by negative 12 will simplify to 1/6, and then x over y squared. And we're going to leave our answer in that implicit form. We're going to leave our answer in terms of both x's and y's. And that's all we do. So the key thing to remember with implicit differentiation is that when you're taking the derivative of a y with respect to x, you're applying the chain rule to that. And so you're taking the derivative of the outer function, and then you have to multiply by the derivative of that y itself. So this was a pretty basic example because all we had was a couple power rules and a pseudo chain rule guy hidden in here. Let's look at a second example where the problem is a little bit more complex, but our ultimate goal is still going to be the same. So in this case now, I have x squared y minus 4x equals 2y. So again, it's obviously not written in terms of y equals f of x. So I'm going to use my implicit differentiation to find the derivative. And as I go and I do the implicit differentiation, again, I need to find the derivative of every single piece. And in this first piece right here, I have x squared y. And so if I want to find the derivative of that piece, because it's x squared y, there's two terms being multiplied together, we have to use our product rule. And again, if you need to break out your product rule and write it in pieces to do your workout, go ahead and do that. So for this one, f would be the x squared, g would be the y, f prime would be 2x, g prime would be, I'm going to call it again dy dx instead of y prime. And then as I go and build the product rule on this, we do f g prime. So I would get x squared dy dx plus f prime g, so 2xy. And so there's my product rule for the first term. And now I'm just going to continue differentiating each piece. Here I have negative 4x. The derivative of negative 4x with respect to x would just be negative 4. Then I'm going to put my equal sign, and the derivative of 2y would be 2, and then dy dx. Because again, if I'm applying the chain rule to that, the derivative of y would be 1, and then I would multiply by that derivative of y with respect to x. Now, what's different about this problem versus our last example is that here we can see we have dy dx's on different sides of our equal sign. And how you choose to go about finishing up the problem is up to you. But your ultimate goal would be, just like in algebra when you're solving for y, you want to get all of your y terms on one side. So here I would get all of my dy dx's on one side and anything without a dy dx on the other side. So I can do this pretty quickly in one step by just subtracting this x squared dy dx all the way over to that other side. And on the left side, be left with just 2xy minus 4. And then here I'd be left with 2 dy dx minus that x squared dy dx. Now I got all of my dy dx's on one side. So what we're going to do now is factor that out as a GCF. Both of those terms on the right side have that dy dx. And if my goal is to solve for dy dx, I need to break it out of there. So I'm going to, on that right-hand side, factor out dy dx. from those two terms. And now once I've broken it off of each of those pieces, now I can solve for that dy dx by dividing by that entire group of 2 minus x squared. And so my final answer for this guy would be dy dx equals 2xy minus 4 over 2 minus x squared. Now, something to keep in mind is that I chose to bring all of my dy dx's over to the right-hand side. And so that kept that 2xy minus 4 the way it was, and it made the right-hand side become 2 minus x squared. If somebody else had solved this problem out, they could have brought this 2 dy dx over to the left side, and we could have had x squared dy dx minus 2 dy dx. And if they bring this guy over here, then they would have had to move both of those over to the other side. So we would have had to subtract the 2xy and add the 4 over to the other side. What this ends up doing is we still get that common factor of dy dx, and we can factor it out just like we did. And now this time I would be dividing both sides by x squared minus 2 to isolate that dy dx. And so if I did it in this method, my answer is going to look a little bit different, and I'm going to rewrite this as 4 minus 2xy. I like to start off with a positive number. So 4 minus 2xy, and then down here, x squared minus 2. These are the exact same values. It's just they're written in terms of factoring out a -1 from both of these expressions here, or factoring out a -1 from both of those there. So if you're solving the problem and checking the answer in the back of the book, and you have a fraction where your terms are exactly the same, except you have all of the signs the opposite. So here, notice I have a positive 2xy minus 4. Over here, it's a positive 4 minus 2xy. Down here, it's 2 minus x squared. Over here, it's x squared minus 2. So if you have the same terms, but every single one has the reverse sign of what the answer key in the back is, your answer is fine. So it's just going to depend on whether you brought your dy dx's over to the left or over to the right. And so just keep that in mind. This answer is just as correct as that answer right there. So we looked at a slightly more complicated problem here by combining in now that product rule with that. And for now, that's what we're going to do. So we're going to kind of, as I said, start with the basics of implicit differentiation. So I gave you 2 basic examples, and your assignment today is going to practice with these. And as we move forward, we'll start putting these in combination with some bigger chain rule problems and maybe some trig derivatives as well. But I want you to get used to just the process. Now, our last goal for today was to also be able to write an equation of a tangent line to one of these implicit functions here. So we're going to wrap up this video by looking at an example where our goal is to write the equation of a tangent line. And the implicit function I'm giving you here, x squared plus y squared equals 25, if you remember back from your conic units section in geometry and pre-calc, that's an equation of a circle. And so they picked a point on that circle, 3, 4, and they want us to write the equation of our tangent line. So we know that in order to write an equation of our tangent line, we need a point, and we have our point, and we need our slope of our tangent line. And we know already that the slope of our tangent line is equal to the derivative of our function at that point. So basically, we want to figure out what is our derivative with respect to x when x is 3. So what we're going to do is go to this implicit function and use our implicit differentiation technique to find its derivative. So I'm going to take the derivative of x squared and get 2x. Take the derivative of y squared and get 2y dy dx. Again, I have to apply the chain rule on my y's. Equals 0. Now, when it's a problem like this where my goal is to write the equation of the tangent line and all I care about is my slope, I usually don't bother solving this guy for dy dx unless it specifically says find me the derivative. I would normally just leave it in its expanded form like this and then replace all of the x's and y's that are in there with their values because it's going to be a lot easier to solve for dy dx and rearrange. So I'm not going to solve for dy dx. I'm just going to leave it in this format, and I'm going to replace x with 3 and y with 4 using the coordinates of my point. So I'm going to get 2 times 3 plus 2 times 4 dy dx equals 0. I can do the math here. This is 6 plus 8 dy dx equals 0. And then I can go ahead and solve for that dy dx. So I would subtract 6 from both sides and then divide by 8. And of course, I would reduce that. So negative 6/8, they're both divisible by 2. That would reduce down to negative 3/4. So now I have my point 3,4 that they so nicely gave to me. And I have my slope of my tangent line at x equals 3, which is now negative 3/4. So I can put all of my pieces together using my point slope formula and write my equation. So today you're just practicing with the basics of implicit differentiation. And your homework is going to be to complete the attached worksheet in our presentation uploaded to Google Drive, or Google Classroom, I mean. And then when you're finished, you want to upload your work to Google Classroom for the worksheet. The answers are on the back. And if you have any questions, please reach out to me.